With this lesson here, I'm trying to mimic how we would learn it if we were in school. When we sort of laid out the whole 3U physics course, so again, Mr. Zer and I team up on things like this. When we got to the waves and sound unit, we thought this was a great unit to kind of change the learning mode and have you discover the topics a bit on your own instead of us just teaching them to you. So when we do it in class, kind of like the Slinky Lab, it's hands-on, you do a little activity, then you learn from it, and after you do the activity, we kind of consolidate your learning. So when creating this lesson, I tried to mimic that style. So in this lesson, and then the next one or two, um, as I typed these things up for you to do at home, I built in little activities. So what I would encourage you to do is when we get to the little activities, pause these videos if you're listening to them to go get the equipment you need, and then try them. They're things you should be able to find in your house. They're things that hopefully will help the learning sort of click into your brain. If that's not your thing, if you don't want to try it, you're just grinding through this and are just going to listen along, then listen to these videos. I'm going to break them up instead of one big monster video. Listen to me talking through this, and hopefully with the text that's typed there and this video clip to go with it, it'll click a little bit better. I'm not tech savvy enough that I can have like audio clips play within this video that I'm making now, so you may choose to pause and watch little video clips or audio clips that I've embedded in the bigger note. And again, if this isn't enough, you can always email me, but this lesson, when I wrote it, I thought in particular, this might be a good one where if you could talk to another classmate about it, that may be more helpful. So if that's your thing, maybe have a friend on a FaceTime or Google Meet or a phone call even, and when you get to something that bothers you, maybe you could talk it through or get through this whole thing and reach out to a friend and see if they agree with everything they learned as well. All right, with that in mind, here we go with part one. In physics, the word elastic has a special meaning. It means that due to like internal forces within the object, that if you were to change the shape of an object that's elastic will snap back to its original, or sometimes we say preferred shape. So an elastic band, if you stretch it, it snaps back to its original shape. The Slinky that we emulated, or that we sort of played with in the last lab, it preferred to be kind of perfectly horizontal. When we wiggled it up or down, it vibrated, trying to get back to its preferred shape, that horizontal shape. Lots of things in physics are elastic, and if things are elastic, it's gonna come up in here eventually. If things are elastic, then they can vibrate, or a fancy word for vibrate is oscillate. So here's what I'd like you to do. Find a ruler, hang it off the edge of a table. You've probably done this in elementary school when you're goofing around, and push down on the end of the ruler so it wobbles up and down. I'm not in the mood to make sound effects, but the link is there. Your ruler is going to make kind of a funny noise. The fact that the ruler is vibrating up and down means that it is elastic. So things that are elastic will vibrate, or if something vibrates, that means it's elastic. The ruler had a preferred shape. It wanted to be mostly horizontal. Maybe it sagged a little bit because of gravity. When you push down on the ruler and pushed it away from horizontal, in a way, it's like it didn't like that. The internal forces wanted to bring it back to normal. If you pushed it down, that makes it wobble upward, and it overshoots its preferred shape and ends up wobbling up and down over and over again. And then it gradually comes to a stop because it's losing energy to create the sound that you heard, and it's going to be a little bit warmer. When something wobbles, we quantify how quickly it's wobbling with a word called frequency. So when something vibrates instead of wobbles, so the end of the ruler was vibrating up and down. It's moving. We could talk about how much distance it travels in a particular time, but that's a weird kind of speed to quantify for something that's vibrating. We wouldn't use our regular meters per second because it speeds up and it slows down as it's wobbling. So to quantify how quickly something wobbles, we've got a new quantity. It's called frequency, and it literally is the number of vibrations that happened in a second. Or we're going to call frequency letter F. So it's the number of vibrations that had it in time. So frequency is going to be number over time. If the end of your ruler went up and down 40 times in a second, we would say that it had a frequency of 40 vibrations per second. Per second is sort of the right unit, but we've replaced per second with hertz. So if you ever heard about something quantified in the number of hertz, it's talking about how quickly that object can vibrate, or we've started using it in other places. Like if you buy a new phone or a new computer, they'll program the processor of those electronics to crank through a simple calculation as quickly as possible. So it's not a mechanical vibration, it's just doing a little job over and over and over again. And it'll say how quickly that thing is doing that job, and usually it's gigahertz these days. Giga means billion. So how many billion operations it does per second. For us, it's just going to be the number of wobbles per second. If the end of your ruler went up and down 40 times per second, we're going to say it's got a frequency of 40. Here's a little thing. If it went up and down 100 times in half a second, then the frequency would be 100 as the number of times divided by 0.5 for the half a second. That would work out to 200, and we give it the unit of hertz. We're going to start talking about sound a bit more and more. Our ears hear frequency as pitch, the highness or lowness of the noise. Take your ruler and hold it in the exact same position, but put more energy into the vibration. Maybe push it down farther before you let go of it, or the opposite, push it down less far and let go of it. What changes when you do that? Does the pitch change, the highness or the lowness, or does the volume change, how loud it is? Give it a try. Peeking ahead, the answer is right here. If you only change how hard you push into it, basically changing the energy that you put into the wave, then it would have the same frequency, but it would be louder. So amplitude came up in the Slinky lab. Basically, when you push the ruler down more, you're increasing the amplitude. And what we can see is that when you increase the amplitude like that, you change the volume. This isn't kind of brand new. Not so much anymore with Bluetooth speakers and things, but in the olden days, if you wanted to make something louder, you would connect it to an amplifier. Amplitude is connected to volume. All right, new thing to try. I'm not going to scroll up so you can actually try it and see if you can come up with the answer before I show it to you. Take your ruler again, and now change your ruler so that more of the ruler is hanging off the table or counter or whatever you've got it on. So get your ruler, have more ruler hang off. What happens when you vibrate it then? Well, the answer was here, sorry. If you hang more ruler off the end of your table, try it if you haven't tried it. With more ruler hanging off the end of the table, you're going to hear a lower pitch, which means it's vibrating at a lower frequency. If I backtrack, amplitude is related to energy, and you were kind of in charge of energy. Put more energy in, you get a louder sound. In this new part, if you can somehow change the shape of the object, so hanging more ruler off, if you can somehow change the shape, that allows you to change the frequency. If you want to be in charge of changing the frequency of how something vibrates, you have to be able to change the shape or the physical properties of that object. You can try this one if you want, just be careful with it. If you had an empty wine glass and tapped it, then that glass is going to vibrate at a particular frequency. But if you add water to the wine glass and then tap it again, since you've changed the physical properties, basically the water makes it harder for the glass to vibrate, it'll vibrate at a different frequency. This is the whole concept behind musical instruments. Musical instruments can play different notes by changing their physical properties. So if you had like a terrible guitar that only had one string. If you change the tension in the string by tightening it, or if you change where you put your finger on the string by changing the length of it, that'll have that string vibrate at different pitches or make different notes. If you had an instrument like a trombone or an old school slide whistle, Google them if you don't know what they are, since they can change their lengths very gradually and basically be any length, they can play virtually any frequency or pitch. So before we said amplitude was related to energy and volume, now we can say frequency is related to the physical properties. If I want to make a louder sound, I have to put in more energy. But if I want to say make a higher pitched sound, then I have to change the thing that's vibrating. And that's all summarized in here. I'm going to pause this video. You can try those questions. And then when we come back, I'll create a second video for part 2 where hopefully you try it, but we're going to do some cool stuff making water waves.